So the last time I formulated the small cancellation condition, and actually now I start with recalling this condition. So we have a sequence of groups. So we have a group G naught, which is the free group, say on a set of generators A with basis A, and we have a sequence of group where each subsequent group is a quotient of the previous group over some set of relators over the normal closure of some set of relators which are denoted R alpha. So alpha is a parameter which is called rank. Alpha is 1, 2, and so on. Here in the sense. So we have the so-called graded presentation. So we have a presentation of the group G infinity, which is defined in the natural way. So this is the direct limit of the sequence of this group. So this is a group of which is given by the set of generators A and the union of all relators R alpha or L alpha. So we have this group, and the main thing is to understand this group G infinity, and we have formulated the small cancellation condition, which consists of several parts. Let me recall it. So we have this condition. So let me just formulate it, because so we need actually some extra notions which occur in this formulation, but I explain them later on. So just okay. So we have this condition. Okay, let's have to recall one more thing. So we have this set of relators, and we have the so we consider for each set of relators, we consider symmetrized set. Symmetrized. R alpha, which means that it's we have a closure on all cyclic shifts of relators, and so taken the inverses. So okay, that's this elements are called relators. R is a relator of rank alpha.
Sorry, I have a small question. So
Yes?
We don't assume that this set R alpha is finite, right? It could be infinite.
Yes. This is actually an important point, because if it would be if you consider only finite set, that it's just, for example, we have in the step. Okay, each step we have a hyperbolic group, and let's see. So, for example, so that's, I do not assume that each R alpha is finite. So it is huge. So in the case of Burnside groups, it's infinite. Okay, so we have this one. Each R is cyclically reduced. So I recall it later on. Used in rank alpha. We have this condition S1, which is for each relator. We have this lower bound on the size of this relator. Okay, this is a spatial length function. This is some parameter omega. Actually, this okay. Actually, I have to write this not for R alpha, but for R hat. Okay, this is not this is a slight difference. It's almost the same. But here I do not have to write R alpha hat because okay we have cyclically reduced. It means that this means that this means that any cyclic shift is reduced. So it doesn't matter which set I write here. But okay, this actually it's better to write this in this way. And this is the main condition. It's formulated in the following way. So this is a main. Okay, this is like a genuine small cancellation condition, but it's formulated not in terms of common part of relators, but it's formulated in terms of closed part of relators. So if say R1, R2 are relators, and they have a closed parts. So this means that if we have this, so this is a graphical equality. Ri is equal to, so this is like a starting segment of Ri, and we have S1 is equal to U S2 V in G alpha minus 1, so in the previous group, and UV are special words which are called bridges. So bridges of rank alpha minus 1. So we have this equality, and if so, this we could have closed parts of two relators. So this equality means that they're close in this group, close in rank alpha minus 1. So then, okay, now I need one more condition. S1 is sufficiently large compared to the size of the whole relator. And you see that here I use this special length function. And okay, and the conclusion is that actually these relators are conjugate R1 and conjugate with the same U here. R2 U minus 1 in G alpha minus 4. So this is okay, this is the small cancellation condition. And okay, I have to explain the things which are used in this, the notions which are used in this conditions. So first of all, what does it mean to be cyclically reduced? Cyclically reduced means a word is cyclically reduced if any cyclic shift is reduced, as I already told. But what does it mean to be reduced? So reduced in rank alpha. So X is okay. Actually, I have to first of all I have to define this set. So this is H alpha. This is the set of all the so-called breaches of rank alpha, and this is it's defined in the following way. So it's the set of all words U, say P, V, where okay U and V are in the previous rank. So bridges of the previous rank, and P is a subword over later. Okay, that's like let me just write in this way. U, okay, PQ is a some relator. This is one thing. Okay, this means that this is defined by recursion, and we need to define H0, H0 is just this consists from the empty word. This means that okay, we have this unique bridge of rank 0. So that's it. So this means that okay, these bridges are the main role of bridges is to be used in the relations which are show these relations of closeness relations in the corresponding group. So okay, these two words x, y are called close in rank alpha if x, so if for some u and v we have this equality, so we have this similar thing here. So we have closeness in rank alpha minus 1 here. But okay, the point is that this u is the same as this u here. And what else? Okay, and I have to recall this one reduced. So x is, okay, I denote it in this way, reduced in rank alpha. By definition, if and only if x is reduced in the previous rank, and if we consider any subword of this word, x1 say as x2, where x is close to some subword of a relator, which actually I call piece, okay, u or p v, where in the previous group, and so let me just say, as I already have this one, s is close in rank alpha minus 1 to some p where r is, which is a subword of a relator, then actually we have p, the size of p is less or equal than some parameter rho times the size of r of the whole relator. So this is an analog of then reduced word, but rho is actually okay. It can be actually taken like close to one half, but I have this one I have this another value for this parameter. This is I take this one 9 lambda. So lambda is another thing. It's a main parameter of the small cancellation here. So this is sufficiently small. So the rho is actually, if lambda is very small, this is close to 1. Anyway, so this means that x doesn't contain a subword which is close to a very large part of a relator. And okay, that's another point is that I use this length function, which is not just the length of the word. And actually, I have to recall this one. So I recalled everything which is in here except this length function. I do not want to recall the whole definition. So I defined it in the previous lecture, in the previous talk. Sorry, but just I recall the idea. So the idea of defining this one. So we have this size in rank alpha of a word x. So the idea is if you have a word x and we consider partition of x into parts, and each partition part, each partition subword is either a letter or is close in appropriate rank to a piece of an appropriate rank. For example, if we consider say some S which is close to, actually I draw a picture now. S is U, say P, V, and P is a P so P is a piece of rank alpha, so is a subroad of rank of a relator of rank alpha. So the P like this here. So if we have this, if this happens, so we have subroad S like this, then we consider we assign to S the length, the size 1. So actually it can be very long word, because we can have infinitely many relations of rank alpha, so P can be very long, and S consequently can be very long. For example, P can be just graphically equal to S, so it can be very long subroad. But we anyway we measure this subroad as of size. We assign this to this subroad size 1. So we consider partitions of this sort. So this is P, a piece of rank alpha. And okay, this is the same thing. So if we have a piece of rank alpha and S like this, and okay, so we have P and S are close in rank alpha minus 1, then we count this as size 1. If we consider if we have the similar subroad, but not in rank alpha, but in rank alpha minus 1, then we count this for the size of this word with the coefficient which is zeta, which is okay, I take it to 1/20. So this is some coefficient. And if you have a similar S, but not in rank alpha, but in rank alpha minus 2, then we count this with coefficient zeta square and so on. So this and if you have just there's a plain letter, so it was a word of length 1, we count this with coefficient with weight zeta to the alpha. Okay, this is very small value. Okay, this is like a so we have this size of the word in rank alpha. So like a distorted size, weighted size, when large pieces of the word can have like size 1, another. Okay, so this is like not the definition, just the explanation. So the idea. Okay. And okay, that's I recalled all this stuff here. So what I'm going to talk about today is actually okay. That's what is it for? What is these conditions for? So I claim that I want to formulate some things. First of all, we have this kind of small cancellation condition, and with an appropriate choice of parameters. And okay, that's parameters are. So we have several parameters here. We have omega parameter, lambda parameter, and this is another parameter which is actually the value of zeta is fixed, and we have rho here, which the value also fixed, and also we have to be a true small cancellation group. We have another condition on parameters which are so lambda is less or equal 1/24, and lambda times omega is greater or equal than, I think, 20 as far as I remember. So we have this. So under these conditions, we have some properties of these groups, which are really small, which show that this is a really small cancellation group. So which are there are analogs of the small consequences of usual small cancellation conditions. But okay, but before formulating them, let's actually look at these conditions, and we see that they all depend on the value of rank alpha. So I assume, of course, that all these conditions are hold for all alpha greater or equal than started from 1. Okay. So this is now we have this if we have this group sequence of groups. Actually, I even do not assume that alpha is just the set of all natural numbers. It can be a finite segment of finite subset of natural numbers, but I don't care. So actually, usually I assume that alpha, all possible values of rank are all natural numbers here. So I assume, and then I assume that these conditions hold for all values of rank starting from 1. Okay, let me actually free some space here. So this is a okay. I recall this. So this is I assume that we remember the definition of the bridge words and closeness. Okay. I keep this one. For example, under these conditions, we have a generalized then property. So let's formulate it like a theorem. So under that's under these conditions. How can we formulate the generalized then property? Actually, I just tried this simple formulation, and we see that it's really it's really like a then property. So if x is equal to 1, no. If x is reduced and x is non-empty, so we have a non-empty word which is reduced in rank alpha, then x doesn't equal to 1 in G alpha. Okay, let's first of all I would like to remark that all the things we formulated is just for this not for the whole group G infinity, but I formulate this for this sequence, for each group in this sequence. And for example, if you can generalize this, from this it follows if x is reduced in all ranks and non-empty, then it cannot be it cannot equal to 1 in this group. But okay, but anyway, let's look at this property. Okay, so that actually we can reformulate this. So if you look at the definition of equivalently, if we look at the definition of the reduced in rank alpha word, then I can reformulate it as follows. If so, it's have a contraposition. If x is equal to 1 in G alpha and x non-empty, and if x is reduced in the previous rank, then we have this one. Then x contains a subword S, which is S like this one. S is close, and I just in the previous group in rank alpha minus 1 to some P, which is a subword of some relator, and the size of P is greater than rho times the size of alpha minus 1. So okay, let's look at this. So again, as I said, if lambda is quite small, but okay, it's enough to consider this condition on lambda. So it's 1 over 24, 9 over 24. It will be 3 over 8. So if rho is then if lambda is equal 1 over 24, then rho is 5 over 8. So it's more than a half, and we see that S is close, and S is a subworld of X, which is close in rank alpha minus 1 to some P, and P is greater than at least 5 over 8 of the whole size of the relator. So it's a similar, it's an analog of the of the usual then property. So generalized then property. And okay, instead of in the standard then property we have a subword which is also a subword of a relator, but we have a subword which is close to a subword of a relator. So coincidence is replaced by closeness. So this is okay. Here. So okay, this is a typical statement of the small cancellation theory, and we can have more. We can have more consequences of this small cancellation condition, and I will talk about them a little bit later. So there's more consequences. But okay, another thing. So actually, this why I introduced this condition. That the point is, of course, that I would like to apply these conditions to the Burnside groups. So this we have, and actually the main result which I would like to formulate is this theorem. If so, we consider the Burnside group, so which is traditionally denoted by BMN. And which is defined by, so it's an M-generated free Burnside group of exponent n, which means that we have this one, M generators, and relators are all the relators are of the form for, so it's identity relation. So this is the Burnside group. So BMN satisfies. So okay, no. There is okay. We have to find a special set of relations of defining relations for the Burnside group. So there exist sets. Okay, R alpha of the form. All the relators should have this form, nth power. For where x runs some set. Okay, so let's denote it by En. So there exist sets of this form, such that this group is precisely. So this is the limit of all these groups here, and satisfies and this small cancellation condition hold for some particular values of these parameters. And as far as I remember, we have lambda is 80 over n, and omega is like 0.1. Okay, actually n over 4. This one. So it's not so important. It's not so important which particular values are of these parameters, but we can actually check this this equality, this bounds. So we have, okay, there exists, okay, the main condition actually for if n is started from 2000s is odd. The main condition is this. So 80 over 8 over 2000 will be 1 over 25, right? Yes, yes. Okay, this we have here, and if it's 80 times, okay, we have precisely 20 here. Okay. So this is actually the main result. It says that the Burnside group can be represented as this small cancellation group when we consider this version of the small cancellation of the iterated small cancellation condition. In the remaining part of my series of talk, actually, I would like to explain why this is true. And also, I would like to formulate some more consequences of the small cancellation, of the small more consequences like this of the small cancellation of this iterated small cancellation condition. So, okay, but before talking about this, I would like to. More to consider. Okay, let me formulate one more consequence. So this is one thing, but actually this is very useful. I mean this is generalized this condition is one thing, and actually we need more. Okay, we need more statements about this small cancellation group. And another one, for example, is the following. Okay, I have no room here. Okay, this is the theorem. I formulated this theorem, and okay, I would like to erase it immediately. So the formulation is simple. The Burnside group under this condition when n is odd and it's greater than 2000. Of course, we can say greater or equal, but it's the same thing. It's greater than 2000. 2000. Then there is a set of defining. There is a great representation for this group which satisfies these conditions. Okay, another consequence. I actually mentioned this. I mentioned the consequence of the standard small cancellation condition, and I call them single bigons and trigons are single layered bigons. For example, let's formulate this one. Bigons are single layered. So this means the following thing. If you consider two words, and if you assume that we have this equality in this group, and such that both words are reduced in rank F. Okay, let's consider the corresponding diagram. Which means that we have a Van Kempen diagram with boundary loop. So we have a disk diagram, and boundary loop is labeled by x, y to the minus 1. I can draw this the picture like this. So I have this one, say x, and because we have y to the minus 1, we can draw this in this way. We have y here. So I draw labels over some sections of the corresponding sections of the boundary loop of the Van diagram, and we can see that each cell of rank alpha of this diagram. So we can see that each alpha cell. So in the standard, if you have a standard small cancellation condition, this property goes as single layer. It means that each cell, each two cell of the diagram has a common piece of the boundary with one section, with x section, and with y section. So the corresponding diagram looks like this. So I draw this picture, something like this. So this means single layer. But in the case of this on this iterated small cancellation, we don't have a common piece of boundaries, but we have a closed piece of boundaries. So we have this. And the corresponding statement should be formulated in the following way. Then let say delta be some reduced diagram over the presentation of this group over the corresponding. Okay, let me just write it over G alpha, which corresponds to this relation with label x, y to the minus 1. And then each alpha cell, this is okay. It's alpha cell means that we have a cell which is labeled by a relator of rank alpha. Has a contiguity subdiagram to either to x section and y section. To the x section and to the y section. You see that I have to to formulate this property. I have to introduce several more notions, like what does it mean for a diagram to be reduced. Okay, that's this is probably I would not like to define this. To define formally all this stuff here, but okay, the reduced diagram means that the diagram doesn't have a cancelable pair of cell slots, and I have to introduce what does it mean to define what is a contiguity subdiagram. But okay, that's but actually, in our sense, it's a very simple thing. It's a subdiagram which has which consists of 4 sections of the boundary. So we have we have a section which belongs to which is a subworld. Here we have a section which is a subworld, which is a subpath of this y section. Another section of the boundary of the subdiagram is a subpath of the boundary of the cell, of the corresponding alpha cell, and we have two another sections of the boundary, which actually we only require that they are labeled by bridges of rank alpha minus 1, and this is inside, and the whole this subdiagram is consists of only cells of ranks not greater than alpha minus 1. So this is very similar to the notion of the contiguity subdiagram in Alshansky approach to the Burnside group. So if you so I hope that some of you know this notion of the contiguity subdiagram in the sense of Alshansky. His definition is a little bit more complicated, so there is a special requirement that to have this so-called I don't remember the name. So we have some cells inside which are called bonds. Okay, I remember they are called bonds. But anyway, but I require that which have just the pieces of bonds. So we have a similar thing, but this contiguity subdiagram precisely corresponds to our notion of closeness. So we have two. So we consider this boundary of the contiguity subdiagram, and we consider the label, and we get a relation which is precisely which corresponds to the closeness. So we have one word, we have another word, and they are close in rank alpha minus 1 because we have a subdiagram of rank of rank alpha minus 1, which means that we don't have cells of rank more than alpha minus 1 here. So other questions about this? So you see that I have to. You see that we have this. We have a very quite simple formulation of the generalization of the generalized then property here. So it can be formulated in terms we already defined before. But for example, to formulate this one, bygons are single layered. We need to introduce more things here. We need to introduce the notion of reduced diagram. We have to introduce the notion of a contiguity subdiagram and so on. So we have this. But actually, what I want to do is just to give an example of what other consequences of the small cancellation condition can we have in this generalized small cancellation sphere. Okay. Yes, of course, давайте по-русски. Конечно, да. Нет, alpha, in general, are infinite.
Даже бесконечные могут быть?
Абсолютно, да.
А тогда алгоритмически мы не всегда сможем проверить вот x равно y, если у нас там бесконечное число этих r-альфа.
Ну, вы знаете, нет, на самом деле можем проверить алгоритмически, если... Ну, дело в том, что там если мы сумеем длину хорошо ограничить. Вот, если мы можем ограничить длину, вот это, здесь понятно, здесь мы можем всегда ограничить длину, потому что здесь под слово, да? А если мы можем ограничить длину вот этого куска, можно это все сделать, там это формулируется утверждение соответствующее. Вот, на самом деле можно длину ограничить, и это, так сказать, не... Да, бесконечные, да. En, so R alpha in the case of Burnside groups are infinite, and this is an important thing. So I explain this later why they should be taken infinite here. Yes. Actually, there are two different ways of how to define this R alpha in Alshansky style. In his initial paper, R alpha consisted precisely of one relator. In his book, he takes all the relators of the minimal possible lengths actually. and there are finitely many, of course, because the length is fixed. Okay, okay, that's okay. This is an example, and actually, what I want. Okay, let me try to to say something in in a more very informal way. So we have three languages actually. We have three languages of formulating statements in say about this group. And this three language, actually I mentioned these three languages. Let me reserve some place here. So we have languages. So we have a diagram language. Just let me read this one. Diagrams. And this is a typical statement in the diagram language. So we have diagrams, we have cells in the diagram, and each cell has corresponding rank because it corresponds to some each two-dimensional cell has a rank because it corresponds to some particular relator. We have, for example, the notion of reduced diagram. We have partition of the boundary loop of the diagram into sections, and we have also contiguity subdiagrams and so on and so on and so on. This is this is an example of such a statement. We can have so it's like actually I think for Burnside groups it was Arshansky who first used this language. I don't remember how to write correctly his name or something like this. Okay, and we have also language of words and relators, words of relations and relations. A typical example of an approach to Burnside groups which uses only this language. It was initial approach by Novikov and Anyan. Actually, there's a third language, and извините. Greenlinger, yes, you're right, but I mean, if we apply this, if we apply some approach to Burnside groups. So I mean, I'm talking about Burnside groups. And also, actually, there's another language which can be used, which can be very useful, and this is a language of calligraphs. So we consider the calligraph of this, for example, of this group G alpha. We have a set generators alpha, so we have this the calligraph with respect to this already given set of generators. And for example, if we can reflect any statement in about a diagram, we can just we can reflect this. We can reformulate this statement in terms of the calligraph, because if, for example, if we have this kind of diagram, then we can map this diagram directly to the calligraph. So if you fix then the image of just one point, then every path will correspond. Every path in the diagram will correspond to a path in the calligraph, and cells in the diagram will correspond to loops in the calligraph in the natural way, naturally. So we have the similar picture of the calligraph, and we have instead of path in the diagram, we have paths in the calligraph, and okay, for example, the subdiagram like this, which I call contiguity subdiagram, maps to a loop in the calligraph. But this loop in the calligraph consists of is a product of four paths of four sections, which corresponds to sections of the boundary of the subdiagram, and we have a geometric closeness of two paths in the calligraph because we have one path, we have another path, and this is the starting vertices of this path and the ending vertices of these two paths are close in the geometric sense, in the sense that they can be joined by a path which belongs to this bridge, to the set of which can be labeled by a bridge word. This in the sense in the sense I understand. So this is precisely the closeness and geometric closeness in the calligraph. So we have two paths in the calligraph, and the starting points of these two paths and the ending points of these two paths can be joined by paths which are labeled by bridge words, and that I call them close. So we have a closeness in the calligraph. Okay, so we have these three languages. And actually, okay, that's what I wanted to. So they are in a sense interchangeable. So one, as I said, one statement in terms of diagrams can be reformulated in terms of calligraph, and statements in the terms of calligraph can be formulated in terms of word and relations. But okay, but what is a so we can use these three languages, but actually there are different approaches, as I mentioned. So we have an Alshansky approach, which uses the language of diagrams. Almost everywhere he used the language of diagrams. And okay, then there's a Novikov-Adyan approach who is only words and relations and reduced words and some transformations of words and so on. And actually, what is common for all these approaches? And actually, okay, that's I can say that there's another approach which I propose it here, and in the proofs I used all three languages actually. But what is a common thing? There are also several more approaches to which also prove, for example, infiniteness of Burnside groups of sufficiently large exponent. And this approach, okay, let me use this. So-called, it's a kind of generalization of the calligraph approach. So it's a more general. Use action spaces. So it's the calligraph of the group. It's just an example of the space on which the group acts. And okay, this approach, which uses action spaces, again it starts with some space on which the group acts. For example, just the calligraph of the free group, and then using some geometric tools, we at each step we construct a special action space on which the corresponding group G alpha acts, and this is no longer the calligraph. It's some more complicated space. Actually it's a complex with cells of maybe third dimension actually. Okay, but this is a more general thing. But anyway, that's what is common thing. The common thing is this. The common thing is everywhere we we represent the Burnside group as a group with some graded presentation. So we have this sequence of groups, and at each step we add a portion of defining relations and represent the Burnside group as the limit of this sequence of groups. This is a very common thing. So we have no other approach here. And actually, in every approach, we have some kind of small cancellations. So this is an idea which present everywhere. It's very implicit in this approach, and it's more or less. So it can be. It's okay. It's not so explicit in this approach, but anyway, we have everywhere we have a sequence of small cancellation groups. So we have a iterated small cancellation group, but with not the explicit small cancellation condition are not formulated. So they are implicit. They are very implicit in this case. Okay. And what is common? And the common, if once we have this iterated small cancellation group in some in some maybe implicit sense, but we necessarily have this closeness. So closeness is a common feature of all known approaches to Burnside groups, because so for example, if in every actually infiniteness of the Burnside group follows from some generalized then property, and to formulate this then property we need it cannot be formulated in the standard way, like we have a common subord in the standard way, like in the standard small cancellation theory. To formulate this we need closeness, for example, in Anasansky's approach, we have this one. If we have a word which is equal 1 to some group, then we consider the corresponding reduced diagram. Then we have a cell which has a very large contiguity subdiagram to the boundary of the diagram. So we have closeness here because it's formulated in terms of contiguity subdiagram. And what happens, for example, in this approach? Again, in this approach, there's a statement which says that if which formulated precisely in this way are formulated here. So we have a reduced word. Which is non-empty, and then it cannot be equal to the identity. So this is as we have already seen. This is just this is the same. This formulated this generalized then property. But okay, this how we can see, for example, here we can see closeness here. So. Again, suppose we have two words, x and y, which are reduced in some rank, reduced. Not in my sense, but in the sense of Novikov-Adyan. It's a similar thing in rank alpha, and we have equality of these words. Okay, we can draw a picture actually in the calligraph. So we have two words which are reduced, which are equal. In the group, which means that they can be represented by two paths in the calligraph with the same starting and ending point, which are labeled by corresponding words here. So we have this similar picture. So we have two paths. These two paths start at the same vertex of the calligraph, and the end of the same vertex of the calligraph, and they're labeled with the corresponding words which are equal in GL. So okay, and Novikov-Adyan formulated a statement which describes in some sense the equality in the group. So they say that we have a sequence of so-called reversals, and we have the correspondence between so-called I don't remember the English term, regular occurrences. So we have we have one regular occurrence in this word, and we have the corresponding regular occurrence of a subword in another word. So we have these two corresponding occurrences. But if you consider this picture in the calligraph, so it turns out so this the ending and the starting and the ending vertices of this path, which corresponds to this subroutes, can be joined by paths. So these two paths are geometrically close, precisely in my sense. So the starting vertices and the ending vertices of this path can be joined by another path, which are labeled by bridge words actually of rank alpha. So of course, in the case of Novikov-Aydan, this we have some more special conditions of this on these occurrences of this path and so on. But okay, the idea is the same. So this correspondence of regular occurrences of subroutes in this case. This corresponds to geometric closeness. So this we also have closeness in closeness of rods which is important, which plays which plays an important role in the whole theory. So closeness is used everywhere. Okay. And what I would like to say more about this. So closeness is a crucial thing. And okay, so this is the common thing for all known approaches. So we have very similar statements which are formulated, for example, for this small cancellation theory. But now let me now turn to my statement, to my theorem, which I formulated here. So the Burnside group BMN is small cancellation in this sense, satisfies these conditions, and actually I'm slightly cheating here. Okay, let me actually to list components of the proof. So the proof can be informally divided into three parts. So first of all, we have to develop the so-called basic small cancellation theory. Which is actually analysis of diagrams. Over, say, over GL, over this sequence of groups. So we assume that we have this small cancellation condition for some value of rank alpha, and then we develop we prove some consequences of this small cancellation, and some of them are formulated here. In particular, I formulated the generalized then property and formulated this statement which shows that which are called bigons and single layered, and actually we have more. We also have to formulate a similar statement for trigons. So instead of equality of two words in the group, we have to assume that we have a triangle equality xyz equal to 1, and we have a similar statement. The corresponding diagram is single layered, so every cell of rank alpha has a contiguous subdiagram to at least two sections of the corresponding triangle. So this is an example of the correspondence basic small cancellation theory. And another thing, but actually we need much more comprehensive analysis of relations in these groups. So I call it advanced small cancellation theory. an example of a statement of this part is this. For example, consider a statement which should be which of course should be assumed. For example, consider a statement which says that every element of the group G alpha can be represented by a reduced word. So we assume that it should be proved. And it's can be formulated like this: for every word X, there exists another word Y, such that X and Y are equal in the group, and Y is reduced. So every element of the group can be represented by a reduced word. And in the case of the standard small cancellation theory, it's if for the set of reduced words we consider just the set of then reduced words. It's very simple. If we have a subword which shows that it's not, which shows that some word is not then reduced, then that means that we have a subword which is more than a half of a relator, and we can replace it by another part of a relator. We can decrease the length of the word. So it's a very simple thing. But in this case, it turns out that this statement is not trivial. So I do not. I know of no simple proof of this statement. So actually, we need to use some technique to prove this, to prove the statement like this. Okay, so this is an example of the statement which I called, which I include in this part, which I called advanced small cancellation theory. And another thing, and the third thing, the important thing, which constitutes the proof of this theorem, is I could call it periodicity analysis. I will probably talk about this later. So this means, okay, this actually, okay, let us look at these conditions. So we need to show that we have some set of relators for the Burnside group, for which these conditions can be applied, for which these conditions hold. So okay, let's look at this. Why can we show that this condition, the set of relators can be chosen which satisfies this condition? So I formulated this statement which shows that every word can be every element of the group G alpha can be represented by a reduced word, but in a similar way we can prove that every for every x there exists y such that which is conjugate for every x, okay, provided for every x if x has infinite order, for every element of infinite order and G alpha there exists another word y such that x and y are conjugate and such that y is cyclically reduced. So if you know this, and if at each step, at each rank alpha, we add, for example, we want to find some set of relators R alpha, which satisfies this property as 0 here, then of course we use relators which have infinite order in the previous group, in G alpha minus 1, and because of this statement in rank G alpha minus 1, we can represent them by cyclically reduced I'm sorry, actually, in rank alpha minus 1, of course, because it cannot be reduced in rank alpha. So this is okay. Misprint here. This is a typo. Okay. Of course, every relator should be reduced in the previous rank. So okay, we apply this statement for the previous rank, and we get we can represent every new relator by a cyclically reduced word in the previous rank. So this property is provided by this statement. Okay, this property is one. Is provided by the special procedure of defining this set of relators. So this is okay. This actually for now. This is all I can say about this. So it of course means it needed some explanation here. But okay, what I can say more. The point is that okay, there are known several different procedures for choosing the set of defining the set of defining relations for the Burnside group. And there are several ideas. One idea is so-called, for example, if you use this Alshansky approach, then we use the so-called procedure is taken. So we use lengths of the word. So we use each time. So we have assume we have the group G alpha minus 1. Then this procedure, we have the procedure to define the set of relators R alpha. Need to define R alpha, and actually, if you want to use it to define the Burnside group, so we have of course we have to take the periodic relators, and those of the form as already written, they are relators of the form x to the n, where x runs over some set E alpha here. Okay, some periodic relators we need to define, and what's the procedure to choose this? There's a so-called approach by lengths. Actually, if we have this group, then we consider the word of the minimal possible length, which represents the element of infinite order in this group. And okay, we have an option. Either we have one single word of this, or we have all words of this minimal possible length. This doesn't matter. So we define this set R alpha. You state some set of words of minimal possible length, which represents the element of infinite order. So this is the one thing. So choice by length, minimal length. But it turns out if you use this approach, if you use this procedure by length, by minimal length, it turns out that we need to so by length. Need to take very large exponent. So I think this is inevitable. So if you need and this approach which comes from the work of Novikov-Adyan uses so-called procedure by taking the set of next relators by so I could call it by depth. So this procedure choosing okay taken by, okay, consider by depth. This means that on the first level we take all words which do not consist like periodic subwords. This, and we define in this way E1 here. Then for E2 we consider all words which have only one layer of periodic words, so which have a periodic subwords, but so these are so-called of periodic. So we consider periodic we consider words of words in the set which contains periodicity of only of depth 1. On the next level, we consider words which contains periodicity of level of depth 2 and so on. So this is the idea. Okay, this what I said, of course, is very informal, but I can say about this a little bit. I can say about this more. But okay, that's this. And if you have this approach by taking the set R alpha by depth, then actually we can have more optimal bound for the exponent. So this is an essential thing here. So this is what I can say for now for this property S1. And about for S2, we have this part of the proof which called periodicity analysis. So what we have here, we have two periodic relators, R1 and R2, which are of this form here, and we have we have subwords of these relators which are close in the group of the previous rank here. So we need to make some analysis of relations of this form. We have one periodic word, another periodic word. Okay, you see that we have lambda here, which actually means that we have some numbers of relators, some number of periods in S1 and S2, because we have these large periodic relators. So we have to make some analysis of relations of this sort, and this is okay. That's S2 is provided by this part. By periodicity analysis. And actually, to make this analysis, we need this part which I called advanced small cancellation theory. And actually, I was a little bit cheating here, because to make this advanced to give this advanced small cancellations to establish this advanced small cancellation theory, we need, for example, analysis of conjugation relations in the group. And actually, we need one more condition, so which did not write here, but actually now I'm writing here. And this condition I call, okay, let me denote it by S3 here. So actually, I'm considering small cancellation group which satisfy not only these two conditions, but one more condition which let me denote it by S3. And this condition is this: if you take any relator, then this relator and its inverse are not conjugate. In the previous group. So why this condition is so important? For example, consider some relation of which represents some relation of conjugation of two elements in the group G alpha. So suppose we have X is equal to, say, Z to the -1 YZ in this group. Okay, if we want to analyze this relation, then we draw a annular diagram of a representation of the group G alpha. So we have a diagram like this. We have a we have an annular diagram, and one boundary loop of this diagram is labeled by X, and another one boundary loop of this diagram is labeled by 1. And of course, to analyze this diagram, we need make this diagram reduced. So we cancel all possible cancelable pairs of this diagram. But it can turn out that we have a cancelable pair. We have a cell which form a cancelable pair with itself. So let me draw a cell like this. So this is a cell which is labeled by a relator of rank alpha here, and it has a large common part which it has two pieces of the boundary of the cells which are close. So which can form contiguity subdiagram here, and so we have so it's possible we can have this situation, but there is no cancelable pair. So we have a diagram which is not reduced because so we have a cell which have a large contiguity of the boundary with itself. So this is a bet for analysis. That is a bet for small cancellation. But we cannot do something with this diagram, because there is no cancelable pair of cells here. And this situation corresponds so if you apply this condition as S2 small cancellation condition, then we get if you denote the relator which is the label of the boundary of this cell by R, then we from this condition S2 we conclude that R and R inverse are conjugate in the group G alpha minus 1. So this is a bad situation. This situation I call this cell a folded cell, and existence of folded cells needs much more delicate analysis of relations. So this is a very completely another story, and we just assume, so we impose a condition that this never happens, and this condition is this: if you take any relator of rank alpha, then this relator in reverse cannot be conjugate in the previous group. So this, if you assume this condition, that it excludes the situation of the folded cells like this in the diagrams which represent conjugate relations, and this makes it impossible to formulate some properties of conjugate relations in the group. So I assume that this condition holds, and actually the theorem which I formulated, I have to correct the theorem which I formulated, the theorem about Burnside groups, and actually I have to include also this condition as 3 here. So and the point is that actually one of the statements which I prove is this. So it's more or less known, and a statement is this. So it have a proposition. Assume that we have already the group which which satisfies, so is under condition S naught S3 for up to say say alpha minus 1. So we have the previous group. The previous group G alpha minus 1 is a small cancellation group in our sense. Assume that each relator of the rank alpha has the form some r naught to the n, which is okay. Which can be different for each r, where n is odd and r naught is a non-power, which of course means that it cannot be represented as a non-trivial power in G alpha minus 1. So if each relator has the form, then this property S3 holds. So to satisfy this property, to satisfy this condition, we need only that every relator of rank alpha has the form is an odd power. So this for automatically for the Burnside groups of odd exponents satisfies this condition, and we have this condition as automatically satisfied. And another equivalent form of this condition, this group doesn't have involutions. So involutions make life much more complicated, and in the case of Burnside group of odd exponents, there are no involutions here. So we have this condition. So and I think that this is a good point to stop for today. So I tried to what I tried to do is to list some parts of the proof of the result I formulated, and maybe I will say so. This is most important part, and I think I hope I will speak one more time. And actually, I would like to say something about this periodicity analysis. So we assume that we have a small cancellation group in our sense, and how to analyze relations. We have two periodic words, and these periodic words are close in the group in the corresponding sense in what we conclude from this. So in some sense, in some informal sense, we have to generalize a known statement about overlapping of two periodic words. So we have this. There is a very well-known statement. If we have two periodic words and they have a large common overlapping part, so which contains for at least two periods of each of the periodicity, then actually this periodicity can be these two periodic words can be glued together to form periodic words with a single period. So this is a known statement, and actually we have to generalize this statement in our situation. In our situation for this, when we instead of overlapping, we have close words. So, and this is all for today. If you have questions, then I can answer.